Now that we learned that an amplitude is the half of the distance between the highest and lowest point of your sinusoidal function, we're going to look at something called a period, which is another characteristic of sinusoidal functions. And what a period is just the length of the shortest interval along the x-axis, so it's a horizontal distance, before and after which the y values repeat. So it's basically the length of one full cycle of your wave, and you can start that cycle at any point. So for example, in this diagram let's say I start here, and you basically trace your curve, your wave, until you get to the exact same point before your graph starts repeating. So that horizontal distance is one period. And again, you don't have to start there. For example, if I start here, right, I go down, I come back up, and even though I hit this same point again, my graph doesn't repeat yet, right? It keeps going up, and it doesn't repeat until it gets to this point right here, where it starts to go down again. Okay, so this from here to here is also one period, and it is the same as this distance that we measured up top. So the easiest ways to see it might be to pick two high points, and the distance between that horizontally is your period, or to pick two low points before it repeats, and this is also one period. So that's how you identify what a period is on the graph. Algebraically, on the equation, b is going to help us calculate period. So remember we had said b is applied to the x and we're multiplying, so that's going to be horizontal stretch or compression. Okay, so you think of this diagram right here. You take your sine wave and you stretch it horizontally. Well, then your period is going to be longer, right? If you stretch it horizontally. Or if you compress it horizontally, then your period is going to get smaller. So the period can be calculated using the equation by doing 2 pi divided by the absolute value of b. We keep the absolute value there just because we know that if b is negative, it just means a reflection. So it's basically just 2 pi divided by b would give us the period. Let's look at an example. We want to identify the period in each of the sinusoidal functions below. So here we have the parent function y equals sine of x, and we want to identify a period. Now all of these problems also have frequency, which is what we're going to look at next, and then we're going to come back to them and fill in the frequency. So right now you just have to worry about period. Okay, so b is the number right in front of the x in the function, and in this case it is 1. Okay, so according to my equation, 2 pi divided by b is going to give me my period. So the period is 2 pi, which means that my graph repeats after 2 pi. So if I start at 0, 0, okay, and I start tracing my graph, here's 1 pi, a little bit past 3. Remember, pi is right here. Okay, and then I keep going, and here is 2 pi. And sure enough, it starts to go up again after 2 pi. So one full cycle is 2 pi. Okay, and that is one period, is one full cycle. Notice that the graph of sine of x resembles a wave pattern repeating itself every 2 pi radians. And so for this reason, because it repeats every period of 2 pi, we also call the sine of x function a periodic function with a period of 2 pi. And certainly the period of sinusoidal functions doesn't always have to be 2 pi, depending on how we stretch or compress it horizontally, but they're all going to be periodic, right? They're going to start repeating after a period of time. In this case, it starts repeating after 2 pi. So I want you to pause the video, and I want you to try B and C, looking at the equation and looking at the graph, identify the period. All right, let's come back to check your work. So according to looking at my equation, B is 2. So my period is going to be 2 pi over 2, which simplifies to pi. And you can see on the graph that If I start at 0, 0, and I trace the graph until it starts repeating again, one full circle is exactly pi, a little bit past 3. And then 2 pi, if I go another cycle, I'll get to 2 pi. And then for C, B, the B value is 1/2, right? So we've got 2 pi divided by 1/2, keep change flip, 2 pi times 2 is 4 pi, which tells us that it takes 4 pi units to complete one full circle. So from 0, 0 to 2 pi, I can see that it takes, I've gone half a cycle. Okay, but if I go 2 pi to the left of 0, 0, so negative 2 pi, here is my one full cycle before it starts repeating again. And this distance is 4 pi, which is my period. And makes sense for, in terms of, you think about it, thinking of horizontal stretches and compressions, right? That first one, when I multiply x by 2, I'm really compressing horizontally by scale factor 1/2. So I'm taking my sine function and I'm compressing this way, which means I can fit more cycles in a 2 pi period. Whereas in the example C, I'm multiplying x by 1/2, which everything applied to x is opposites according to transformations. It's really a horizontal stretch by 2. So if I'm taking my sine function, my parent function, and stretching it horizontally, then it's going to take a longer time to complete one full cycle. All right, now let's take a look at frequency. The frequency of a sinusoidal function is the number of complete cycles that the function completes in an interval of 2 pi units long. So basically, how frequently can I draw a cycle, one full cycle of my sine wave in a 2 pi unit long period, right? And so the frequency, it is just b in my equation. So that's very easy to tell. Frequency is just b, and I put the absolute value of b just to remind us that if there's a negative, that's just a reflection over the y-axis. Doesn't have anything to do with the frequency of the period. So period is just b, very easy to identify from the equation. And from your graph, if let's say 2 pi is right here, okay, in a period of 2 pi, according to this sinusoidal function, it looks like we've completed one full cycle before it starts repeating again, another full cycle, okay, and then a half of a cycle. So in this case, the frequency, I would say, is 2.5 because it completed 2.5 cycles, full cycles of my sine wave. So again, I want you to pause the video and I want you guys to go back to the previous 3 examples and identify the frequency, which should be a little bit easier. And one more thing, this formula, frequency, is just also true. Frequency is 2 pi divided by the period. This and the other formula to find period, 2 pi divided by b, is interchangeable. Most of the time we're going to be using b to help us find period and not the other way around, because usually we can tell what the b value, the frequency, is from the equation. Alright, so pause the video and go back to the previous 3 examples and fill in the frequency and then come back and check your work. So for this first one, frequency is just b. B is the number in front of the x in the sine function, so it is just 1, which tells me that I can draw one full cycle in a period of 2 pi units. In the second one, my b is 2, so that means my frequency is 2, and I can tell that I can draw 2 full cycles. Here's one, and here's the second one, in a 2 pi period. Okay, and then this last one, my b value is 1/2, so my frequency is 1/2, which means I can only draw half of a full cycle in a 2 pi period. All right, so here's a summarizer problem that combines everything that we've gone over in this section. Again, I want you to pause. I want you to try to sketch the graph, identify the amplitude, the period, and the frequency. Okay, identifying the 3 pieces of information from the equation should be pretty easy. Graphing might be a little bit tricky, right? So amplitude is the A value, number in front of the sign, so that's 4. So I know that my high point and low point is going to be at 4 and -4. And my period is 2 pi over b. In this case, b is 2. So 2 pi over 2 is pi, which means that I should be able to fit 1 full cycle of my wave from 0 to pi in this section right here. And the frequency is 2, meaning that from 0 to 2 pi in a 2 pi period, I can fit 2 cycles, which makes sense, right? So I need to squeeze 1 full cycle of the wave between 0 and pi, and then just keep repeating that. And so I'm going to start with the x-intercepts. That's not going to change. 0, 0 is not going to change. And since I am squishing it, compressing it horizontally, I know that this point right here at pi is going to be at the same spot before its repeat, right? And then pi over 2 is another x-intercept, and it's going to be my new x-intercept. And then in between, I need to have a high point and a low point. So the high point is going to be the halfway point between pi over 2, which is pi over 4. So like right here, pi over 4, we're going to be at 4. And then right here, halfway point between pi over 2 and pi, we're going to be at -4. And so that's my sine wave. It starts at 0, 0, it goes up, hits a high point, and then comes back down, hits an x-intercept, goes down, hits a low point, and then comes back up, hits the x-axis, and then it repeats again. So we can do the same thing. 4, 0, -4, 0. And here is another cycle, right? And then we can do the same thing to the left. Got -4, 0, 4, 0. Here's one more cycle this way. Remember, these graphs don't have to be perfect. Just a sketch. And then here's one full cycle, and then if I want to keep going, we can certainly keep going back down to -4, 0, 4, and then -2 pi will be another cycle. All right, so there it is. That is your function y equals 4 sine of 2x, and if we have described the transformations, it is being vertically stretched by a scale factor of 4, so the amplitude is 4. Distance from the middle to the high point is 4, and so is the distance from the middle to the low point. That's the amplitude, that's 4. And the middle, my midline or the wave axis stays at y equals 0 because I did not shift my parent function up or down, so it's going to stay right there unless there is a vertical shift. And then we have pi is 1 period, so if I look at this distance between the 2 low points, this will be pi units, and then we can fit 2 full cycles in a period of 2 pi, so the frequency is 2.